Okay, a small moment more, but let's welcome David Rowley, major contributor of Postgres, for his presentation on writing fast C code for a modern CPU. Oh, and applying it in PostgreSQL. Let's give him a hand.
Thank you. Thanks for coming, everybody. So today, as Matthias said, writing fast C code for a modern CPU and applying that to Postgres. And I'm glad I put that in brackets because it does take me a little while to get back around to Postgres. Okay, I think I have this. So, yep, my name's David Rowley. I've been a Postgres contributor for about 12 years, and I think you could say I'm probably addicted to performance stuff. So I've written a few things that I've done over the years down there, and it's pretty much mostly performance stuff. So just to set the scene for today, if you're a DBA and you want to make Postgres go faster, you're probably going to start with tuning PostgreSQL config. This is from a CPU point of view. You might increase work mem, something like that. And then you're probably going to move on to rewriting your queries, adding indexes, and maybe extended statistics, things like that. And assuming you're not going to upgrade the hardware, you're probably going to run out of stuff that you can actually tune in terms of CPU. And then you have to become a Postgres hacker, and you have to do something like modify some algorithms, get rid of some linear lookups, and maybe use something like a hash table or something like that. You might then decide to work on the query planner. I've tried to put these in order of sort of least common to change. You might do something with the query planner and make it do something that previously didn't. And then you think you might have run out of stuff to actually optimize. But there's one more, and that's exploiting how modern CPUs work and modifying the code to take that into account. And beyond that, you have to become a compiler hacker and add new optimizations to your compiler. And then you become a CPU designer and you design a better CPU. And after that, it gets slightly less common. I mean, nobody's going to make Postgres faster by designing a new lithography machine. And then you're all grounded out on the laws of physics, which we assume is fixed and doesn't change. But I have heard theories that it may change depending on where you are in the universe, but I'm pretty happy in this part. So, okay. So I'm going to start with a quote. Jim Keller. Does anybody know who Jim Keller is? Yeah. So he has worked for AMD, Intel, he's worked for Tesla, and he's a CPU designer, quite a prolific one. And he had a hand in doing the x86-64 spec when he worked for AMD. And I think he had a hand in doing the AMD Zen architecture originally. So he said, the limits of performance are the predictability of instructions and data. So let's look at that. Let's start with, what does he mean by this predictability of instructions? So these diagrams, I kind of start with, I don't really like them because they always leave me with more questions than I originally had. But I couldn't really think of another way to start explaining this. So here's a hypothetical CPU, and it's divided into two parts, a front end or a control unit and a back end, which I've not defined. But the front end, which is an important part for the next part of the talk, it's in charge of fetching those instructions in from the program that's running and decoding them. And the decoding is effectively taking those instructions, the opcodes, and decoding them into actual micro opcodes, something the actual backend can execute. And that's not really a one-to-one mapping, like complex instruction sets. You might have a call instruction to call a function, but there's multiple things that go on there. You've got a stack pointer that needs incremented. Then you need to copy the current function name to that new pointer, and then you need to jump to the the actual function that you want to call. So, I don't know what these micro ops are. They're not really documented. These are kind of secrets depending on the CPU vendor. But you can imagine there's lots of 3 different things going on there for that instruction. And that's quite important because you can reduce dependencies by breaking that down more. And that's important because the actual back end of the CPU can execute things in parallel. You've got parallel instructions, So define the back end. Let's not go very complicated at the moment. Actually, it's because of that parallel instructions, maybe it's more like this. Those aren't cores. This is just the ability to execute more than one micro op at the same time. So here's a function that's I took from node ag.c. There's nothing too special about it apart from it easily fits on the slide, and there's a lot of branching going on. So if you can imagine how this, and the CPU is not going to execute this, but we're starting in C here, C because it's slightly easier to understand. But so you might start, the compiled code is going to start here. I know there's 2 lines above this, but effectively, if you look at them, set result to null, test result is null. Like nothing, there's nothing done. The CPU is not, the compiler is going to optimize that away. So it's going to call this function, ag-retrieve hash table in memory, and then it's going to test what the return value of that function was. And then if you're decoding this as a decoder in the front end, you get to this point where you don't know. You want to decode these instructions so they're ready for the back end of the CPU. But you get to the point because you've not actually done that test yet to see what that result was. So you have to make a decision because you want to keep that UOP cache filled up so the back end can actually do work. These are both running at the same time, so if the back end runs out of micro-ops to execute, then there's going to be a stall, and you don't want that to happen because your program slows down. So you get to this point, and something has to speculate which code path it's going to take. And if we look at that as assembly, I'll read this out if you're not too comfortable reading assembly. So the first thing that happens is we push that RBX to free up that register, we push that onto the stack, and then RDI, that's the input parameter to the function, and we move that into the freed up register, RBX, immediately jump to L2. That's an unconditional jump, so there's no test. We just directly jump there, and L2 at the end of the red arrow. We're setting up the call stack for the next function call that, and here we have our first conditional branch. So if you can imagine decoding these instructions, when we get to this jump here, something's got to predict what's actually going to happen. And we don't know, because the following instructions, we need to know what the following instructions are going to be and which ones to decode. So we asked this thing called the branch predictor, which branch should be taken. And it's going to somehow pick one. We don't know how it works yet, but it's going to somehow tell us which one it is, tell the decoder which one that it's going to take, and then we're going to decode the corresponding instructions. But how does that work? So let's read about branch predictors. So this is from Wikipedia, and it tells us early branch predictors that were in Spark and MIPS use single direction static branch prediction. A conditional jump will not be taken, so they always fetch the next sequential instruction. Okay, so you might think that'll probably give us a 50-50 chance of being correct here. Or if you lay out your code in a way that you put the most likely branch as this next sequential instruction, maybe you can get it higher than 50%. But we could do better. So, I mean, this is CPUs back in the 80s, right? The mid-80s, so it's quite a long time ago. So a more advanced static predictor assumes that backwards branches will be taken and that forwards branches won't be taken. And the reason for that is that loops are more likely to loop more than 0 times, supposedly. So that was early branch predictors. Why don't we test a more modern CPU and see how they actually work? So this is a Zen 4 laptop I tested this on. So I've got this function called sumBranchy. It takes this input parameter, an array, and the length of that array. And I've got 2 accumulators here. I want to take the sum of all the negative numbers in this array and the sum of the positive numbers in the array. And you can see within the body of the loop, I'm basically just testing if the element in the array is less than 0, accumulating that in the negative accumulator. Otherwise, stick it in the positive one. And then I'm setting output parameters and returning. So I'll test that. I'll test it just with 1,000 elements from, I'll make it easy, -500 to +499, including 0. I'm going to run that 1 million times, and I'm going to see what the branch predictor predicted. So here you can see branch misses was 0.09% of all branches. So pretty good, not much misprediction there. And this is perfstat, by the way, that I'm using to get this output. So perfstat, and I can run that program, or you can attach to a running PID. So that was pretty easy, right? It was just the sequential numbers. If I give it something more complicated, let's use random numbers. So randomly negative, randomly positive. And we're going to have complete random sequences of negative and positive numbers here, right? In no particular discernible order. Is the branch predictor going to do better or worse? Does anybody have any predictions for the branch predictors? Is it going to do well at this? Does anybody think it's going to do a good job? David? Well, yeah, we're running this 1 million times, right? So, and we'll look at the results. So, the previous to this one, or? Yeah, this is just population of the array. So this is just a function I'm using to populate the array. So then I will just run the sum to get the sum of that array. Right, it's a trick question. So it does very well. So 0.03% of all branches. So how did that work? How did it know? How did it remember all that, right? It must have done that somehow. So, but that was 1,000 elements, so like, what happens if I add more? So I've got 1,000 up to 100,000. And I've brought in another CPU, a Zen 2 from 2019, the Zen 4 is from 2022. So the higher, the worse here, lower the better. So you can see in red, the Zen 4 held on pretty well until 25,000 elements. Then it started getting worse, whereas Zen 2 didn't do as well. And it was pretty bad. There was 12.5% mispredictions by 25,000. So let's look at how a more modern branch predictor actually works. How did it actually do so well here? So one of the ways, and this is not necessarily the way that one of these CPUs work, but one of the ways is to have a branch history register and a pattern history table. And to teach the branch predictor, which is done in the back end of the CPU, when you get to, I've got instructions here. These would actually be UOps, micro-ops. I don't know exactly what those look like because they tend to be secret, but you'll get to this branch. I don't know if it'll be the actual jump or the actual test for the jump. I don't really suppose it matters. So we'll evaluate that. We'll get an answer. In this case, the branch is taken. So we'll shift that history register left one position, and we'll bitwise OR that into the history register. So then we've got a number, right? It's the number 3. So we can just use that as an index into this pattern history table. I've got 4 bits of pattern history, and that I need a 16-element array to actually store all that history to address all those possible combination of bits. So that goes into the corresponding element, and I store the actual result of the branch. In reality, this is probably likely going to be a 2-bit counter, so that effectively it would be a value from 0 to 3 maybe, that when it gets to 3 it doesn't go any higher. And that would mean that when the branch changes, that it has to change twice before it'll change its prediction, which is quite good if you think of breaking out of a loop, which you do once. You don't really want to remember that so that you mispredict the loop the next time you come back around to it. So let's just read a bit more about different, more modern branch predictor algorithms. So this Wikipedia article says, a 2-level adaptive predictor with a globally shared history buffer and a pattern history table is called gshare if it XORs the global history and the branch program counter, and gselect if it concatenates them. And you can see there's a bunch of CPUs, of semi-recent CPUs that use that. And Agner Fogg, who is a Danish university professor, he's got a really good PDF that's free to download about CPU architecture, where he's reverse engineered quite a lot of CPUs in terms of how the branch predictors work and various other parts, instruction latencies. And so he's written, imagine a 2-level predictor with a global branch history register storing the history of the last n branches, which is kind of what I was doing there. I had 4 bits. He said these can often range from 8 to 16 bits. You can imagine if that gets wider, you need that array of history bits to be pretty big. So basically, like gshare will be effectively this, where you'll XOR that result with the actual address of this instruction according to the program counter, and that'll find a new spot in that array. And that'll be more localized, because you can imagine you'll have lots of branches that share the same history pattern. You don't really want that to overwrite the spot in the array. So having that sort of localization of the actual branch itself, moves that off to hopefully a spot in the array that doesn't conflict with another branch that has a matching pattern history. And it's possible that you do have a branch that collides, and that's called branch aliasing, and that happens. And the more branches you have, the more likely that is to happen. So what's the cost of branch misprediction? Let's have a look at that. So to do that, I'm going to write another version of this function that previously had an if test inside the actual loop body of the loop. And I've changed the start here. I've got an array of sums, so a 2-element array, and a 0 that. And instead of having that if test within the body of the loop, I've got this. I'm indexing the array with this, and that's going to return 0 or 1, right? Which is a pretty good index into a 2-element array. So that's going to add on basically the input for the corresponding array element. So effectively a branchless version of that previous function. How does that perform? So you can see in blue here, that's a branchless version, and in green, that is the branchy version of the function. So again, this is testing like 1,000 elements up to 100,000 elements. So by 40,000, you can see the below line. This is in microseconds for one sum of the array, and I'm doing it 1,000,000 times. So it took 60 microseconds for 40,000 and 122 for 80,000. So that's fairly linear performance. But the green line up here, for 80,000, it's pretty much double the performance. So things are going bad with mispredictions. And in red, you can see the misprediction rate. So it's kind of, it correlates. You can definitely see that stuff slows down when we start getting branch mispredictions. And to a point, it's more than twice as slow by the time we get to 100,000 items in the array. So what can we do to actually get rid of that? Like, how can we get rid of misprediction branches? So the first thing, you need to find out where they are, right? And if you run perf list on your laptop, if you've got it installed, it'll give you a bunch of events that the CPU can record. And for me, branch misses is in there. I've looked at recent Intel stuff. I mean, it's a pretty important thing to record, so I'd imagine it's in there, although I've not looked on ARM, any ARM chips to see. So if I pick the instruction, in this case, pick the event that I want to record, branch misses, and use perf record, I'll run that program, and that quite clearly tells me that my sum branchy function was the problem. The branchless version, it wasn't in there, so 100% of the branch misses are coming from sum branchy. What else can we do? So the compiler effectively does a lot of work to actually get rid of these branches. Obviously, it doesn't know if the branch is going to be hard to predict or easy to predict. It's just going to remove branches, and it's going to do its best. So 866-64, we've got a cmove instruction and lots of variants of that cmove instruction. And that can be used to get rid of a lot of branches. Let's have a quick look at that. So this is Compiler Explorer. If you've not used it before, it's really good. I would say it's my favorite website on the internet. It's incredible. So you can input some kind of C program. In this case, I've just got a little function. You can choose which compiler you want to use. There's like hundreds of them. And you can go back like 15 years, 20 years maybe of compilers. And your compile flags. So here I've got just a function, really simple. Take this input parameter, test if it's above 1,000. If it is, return 0 effectively. And you can see here, I'll read this assembly out. So 0 the return register, and compare the input parameter to 1,000, and conditionally move the input parameter into the return register if that comparison is less or equal. So effectively, there's no branching going on there at all. It's completely branchless. And if that condition is false, then this conditional move is not going to do anything. So you can do this without branching. And even more complicated places where I've added a Boolean OR condition. Normally we think of these as, it's only going to execute the second part if the first part's false. But you can see in this case, it's not done that. Effectively, it's taking the input parameter, adding 1,000, comparing that to 2,000. It's zeroing that return register, and then it's doing this conditional move below or equal. So it's using unsigned arithmetic and moving that input parameter into the EAX only if this comparison is true. And if not, it's just going to leave that return register as 0. So it's effectively implementing all that with 0 branching. But obviously, in this case, there's no side effect to doing this. If I put a function call in there, then we can't do that. We need to branch. We can't call that function unconditionally. We only call it when the actual condition is true. So in this case, the compiler was unable to completely remove all branches, but you can see that normally you might have 2 branches for an OR condition, and 1 for each branch of the OR, and the same with AND, because of the short circuiting. In this case, it's only doing 1, and it's only doing 1 actual branch. So there's other things you can do. Here's a function that, or trimmed down version of a function that exists in Postgres. So this function's PG memory is all zeros. And function doesn't look exactly like this. I've modified it. I've also trimmed it down, but I've modified it. And I've added these, the Boolean ORs. And you can see here, if you look at the right-hand side, there's lots of JNE. I'm not going to read this out, but you can see jump not equals. It's pretty, there's a lot of them in there, one for each array element that this is looking at. And this is just unrolling a loop to try and speed this up. But in the Postgres code, it actually looks like this, and it uses bitwise OR. Actually, there's 8 elements that it's comparing in one go. And you can see all those JNEs have pretty much disappeared. It's actually using SSE instructions and starting to vectorize this. It's a bit of auto-vectorization. And if you compile that with march x86 v4, it's actually going to vectorize that up to AVX2 instructions. So that's going to become quite a lot faster. And that's quite a lot of branch removal compared to something like that is how you might write it otherwise. So the other thing that Jim talked about, if we go back to his quote, he did mention and data. And so let's have a quick look at this. So cache prefetching can be accomplished either by hardware or by software. Hardware-based prefetching is typically accomplished by having dedicated hardware mechanism in the processor that watches the stream of instructions or data requested by executing the program, recognizes the next few elements that the program might need based on this stream, and prefetches into the processor's cache. So let's test that. Let's see how good it is. So a slight variation on this. So I've got 2 arrays this time, this input and a positions array of length. And here I'm going to populate them and initialize them just to a sequential number from 0 to the length of the array. I've got another function to shuffle that array. And what I'm going to do is I'm going to shuffle that positions array and effectively randomize the order of it, only the positions array. And here's the code that I'm going to execute. So I want to sum this array, but index it by this positions array. So you can imagine when that positions array is just a sequential number, it's going to access that input array in order that it is actually in memory. But if I shuffle that positions array, the access to input array is going to be effectively randomized. But it's going to be the same code. So I'm going to run this once with the arrays non-shuffled. Then I'm going to shuffle that positions array, and I'm going to run it again and see what the performance difference actually is. So here I've started with 64 kilobytes, and I've scaled this according to the actual size of the array. So this is nanoseconds per kilobyte. So they both start out pretty close, 23 nanoseconds to do one sum of the 64 kilobyte array. But I've doubled this each time up to 1 gigabyte. And you can see something happens around here where the performance just completely tanks. And it ends up 20 times slower by the time it gets to here. So 704 nanoseconds compared to 35 with a sequentially ordered array. So it's pretty massive. And that's just because we're hitting main memory and the hardware predictor just hasn't got a clue what's going on. But with a sequential one, we're still accessing just as much memory, but it's fine. It can access, it can predict the pattern, just a sequential pattern. It's pretty easy to predict. But why would you be so uncaring on your CPU? Why would you have random access to an array like that? And effectively, that's what hash table lookups are going to look like to your CPU. It's, you're not going to sort all the hash values before you actually probe your hash table. They're going to be apparently quite random to the CPU, and it's probably not going to do a good job of actually predicting it. So if I look at Postgres, finally, slide 51, Postgres. I've done the same test effectively. This is a hashed group by, and I've disabled parallelism, and I've made workmem big enough to store the hash table. And I've started off with a 64 kilobyte table again, and doubled it each time up until 1 gigabyte. And you can see, I've scaled this according to the actual size of the array. So in an ideal world, this would just be a very boring graph with just flat bars. But it's not. We still see this slowdown when we get to 32 megabytes, and by 64, we're starting to slow down a lot. If you compare 1 megabyte to 1 gigabyte, 1 gigabyte's about half the speed. And this is, remember, it's scaled per kilobyte, so we're seeing this. The latency a little bit is hidden by the actual calling the hash function. So it's not quite as bad as the previous test case with the 20x, but 2x is still pretty bad. So what can we actually do about that? Like, how can we make that better? So we could use less memory. We can do things like change structs to remove padding. We could use only the size of data the data type that we need. Don't use size t when you could fit it in an int 32, for example. Possibly we could rearrange structs to get rid of padding, although that seems to be quite controversial topic sometimes. We could, and this came up, I heard David DeWitt talking about this morning. Nodes that use workmem, we don't have any awareness of L3 cache. Like, if you think of a hash join, if you give Postgres a gigabyte of workmem, we don't really, we'll just size the hash table and as big as we can until we run out of memory before we start spilling to disk. And we could do probably a better job of making these things more aware of L3 cache. And yes, we have multiple batch hash join, but multiple batching has a lot of overhead. We could be making smaller hash tables and making them more aware of L3 cache size before we actually spill to disk. And that could, speed things up quite a bit. So another thing we could do is help the hardware prefetcher. You saw previously I gave it some access patterns it didn't really like. So there may be things we can do that actually make it easier for the hardware prefetcher. The other thing there is the ability to do software prefetching. GCC and Clang have this built-in prefetch macro, and that just emits a prefetch instruction in x86. And we currently do not use that anywhere in Postgres. And there's probably places we could use that in Postgres. It's kind of hard. If you imagine a sequential scan where you fetch the first tuple in a page, you might think we should just prefetch the second tuple. But if you can imagine that sequential scan is on the outside of a nested loop, and on the inside of the nested loop we do something that takes 10 minutes or half an hour, then was there any point in prefetching that next tuple? In fact, it might just mean that we end up kicking something useful out of cache that might have been useful for something on the inner side of the nested loop. So it's kind of hard. We don't really want to add lots of those if they're going to be useful sometimes and cause problems in other times. But here, just to try and show you that this isn't made up, I was looking at initialization of the plan. So here's a function from nodeag.c. This is done. We call this when we start up the planner, start up the executor, I should say. And the first thing we do here is make node ag state. So basically allocate memory for this aggregate state. And we do a bunch of stuff that might include allocating more memory. And then we do this. We initialize the ag node's subnode, the outer subnode, which basically recursively calls functions similar to this for various other nodes. So you can imagine how that memory has actually been allocated in a memory allocator. This is going to be at the start, and then there's going to be whatever these allocate, and then it's going to allocate memory for all this stuff. And finally, it comes down and allocates a bunch more stuff for the aggregate state. And you can imagine how that's sitting in memory. Everything's sort of fragmented. You've got all this ag state stuff, then you've got stuff related to a bunch of other nodes, and finally you've got all this stuff that was allocated here, and it's all mixed up. What happens if we do this? So I've modified, I just did this on Sunday because I wanted an example. But I changed, like, I don't know, it's 30 or 35 different executor nodes effectively to initialize all that memory just like this. So I've delayed this make node until after calling the subnode, initialization of the subnode. And it meant that I had to effectively just add a variable to store that state because this doesn't exist yet. So if I do that, like, does that help with the performance of the executor? So this is TPC-H, 5 gigabytes, and in blue that's Postgres 18 beta 1, and red is the patched version. So there's a small difference, maybe. I've only tested this on one machine so far, but I run it 10 times. So it's very close to noise, but if I drill into that query 1, and I run it 10 times, if I sort all those 10 results by time and put that in the graph, like at no point was it slower than the unpatched version. So that seems to have made a bit of a difference to the performance. But not very much, so let's try something else. So here's our heap page layout. We've got the header and the start of the item pointer array. And then we populate tuple data from the end of the page. So then we do an insert, we add another tuple. It becomes earlier in the page before the tuple for the first item. And we do another insert, and it keeps populating like that until the page is full. And that looks like that. These item pointers point to that tuple. So if you imagine a sequential scan here, we're sort of walking through those item pointers, item 1, item 2. So you're doing a sequential scan, it's going to be accessing these one by one in a forward memory order. And at the same time, it's going to be accessing these it's going to access these in a backwards memory order. But yet, we have to deform tuples, right, at the same time. So then you deform the tuple, and it starts walking forward before jumping back to the next tuple. And it's effectively an access pattern like that. So what happens if we changed that to become this? And we can't do that all the time, obviously. We don't want to. There's a reason why it is the way it is. But we have something called vacuum freeze. And in theory, we could potentially change the order to this order during vacuum freeze. And if we do that, maybe vacuum needs another option to do this, because I don't think there's enough options in vacuum. I can imagine a utopian future where there's a high commission of vacuum where we have to propose new features, and yeah, I can imagine they might reject that. But so does that work? Like, does it make it any faster? Seems to. If you look at query 9, it went from 10.9 seconds to 6.4 seconds. So that query, there's 22 TPC-H queries, and that one, it does quite a lot of joins. I think there's 4 or 5 joins in that query. Query 1 is effectively just aggregate over one single table, a line items table. But you can see, like, there's no queries that are slower and quite a lot of queries, like that one in particular is significantly faster just from that small change. Yeah, Matthias.
Your Q11 did seem 1 slower.
Ah, yeah, Matthias just pointed out that query 11 is a little bit slower. Good observation. And yeah, maybe it is, maybe it needs more testing. And yeah, I'm not saying we should definitely do this, but I was just trying to emphasize the fact that, this memory access pattern really matters. The question, Greg?
Did you look for something in common between the queries that get faster? In particular, I have a suspicion maybe those are ones that do sequential scans, because that would be reading all the tuples in the order they appear.
Yeah, I haven't done much analysis into that yet, but quite possibly there are ones that do sequential scans. And maybe the number of sequential scans actually matters, because you can imagine I don't know how many different patterns that the CPU can actually track at once, but maybe more sequential scans matters. Query 1 should definitely be a sequential scan. But yeah, I haven't done that analysis yet. But just closing remarks that these memory access patterns, they do matter. The hardware prefetcher, it can only do so much, and the more sequential access, the more likely it's actually going to do a good job. But as far as reducing the memory, that's one way, and we've done a lot of that in the past. Like Jeff Davis worked on reducing the memory for hashed group by quite a lot in PostgreSQL. That's fairly significant. I think it was reduced by 37% by a test that I did a few weeks ago. PG17, we got TID store, which was more like 20x or something like that. It was variable depending on which TIDs you're storing. PG17 also got a bump allocator, so effectively a headless palloc that doesn't have a header. You can't free it, you can't re-palloc it. But it's useful for certain cases where you never need to do that. And like PG16, we got reduced palloc memory overheads, where we took that chunk header from 16 bytes down to 8 bytes, saves memory. And PG15, we reduced the memory in sorts, so that made it quite a bit faster, less likely to spill to disk. Maybe there's some more stuff we can do with the bump allocator. There's a few new things. I think TID store uses a bump allocator to use less memory. John? Yeah, he's nodding. Yeah. So some resources, checklist and resources. Perf list, use perf record the event you care about. Godbolt, I highly recommend it. If you don't read assembly, it makes a lot more sense if you use that cheat sheet. You've got a different register name that's just a lower portion of another register, and if you don't know that, then it's not going to make a lot of sense. And I'm pretty new to reading assembly myself, but that really helped me. Actual opcodes are quite often self-explanatory, although when you get into AVX and stuff like that, I don't know if anybody can learn that stuff. They become pretty spaced out. So there's a bunch of blogs, branchless programming is a big thing. Daniel Lemeyer, who lives around here somewhere, he works in the University of Quebec. He's got a lot of stuff on his website, lemeyer.me. And if you search that for branchless programming, you find a lot of stuff. You kind of get into SIMD territory, single instruction multiple data, when you get into branchless programming. And that gives you much, much bigger speed-ups. There's also branchfree.org, which has kind of gone a bit off topic recently, so you might have to dig a bit deeper. But there's some good stuff in there. So other resources, if you want to learn more about even more recent branch predictors, I've started to get into neural nets and things like that. There's one called Perceptron, I think. I printed out the paper for that with plans to read it on the flight on the way over, and decided sleeping was a better option. The scripts that I use for today to test all the CPU stuff are there. I recommend this book by Fyodor Picus. It's very, very good. And Agner Fogg's microarchitecture stuff, that is really valuable. He's done a huge amount of work to reverse engineer CPUs. And if you just look for random blogs, Chips and Cheese, very good. And here's two GitHub links to the patches I tested in Postgres. And maybe I'll do a bit more work on those for PG19. But I'm happy to take any questions anybody has.
In the results that you showed for the reverse page order,
yeah, these results.
Those results, was that conducted with all of the pages reversed ordered or with some number that would correspond to what you'd expect to be frozen?
No, I reversed them all. Effectively, I modified vacuum freeze and called vacuum freeze. And every page for all those tables, I think there's like 8 TPCH tables, so they were all reversed.
Earlier on when you made the loop branchless by rewriting it, why wasn't the compiler able to do that on its own? Maybe there's some simple reason I don't know that I caught it.
Yeah, that is a good question. I forgot to mention I did compile that with...
Because I felt like that was the twist you were...
I'll keep going back. Because of that.
Okay.
Yeah.
Oh, it says I don't have my specs.
It says 0
Okay.
effectively. So
okay,
I should have mentioned that. I wasn't trying to hide that fact, but like I would have had to find a test case that.
Right. I mean, maybe it actually just would do that.
It does. Like if I compiled that with O2, I mean, I explicitly compiled it with O0. So O2,
it would actually do that.
It would have created a branchless version of that, but that would have made it harder for me to actually talk about it.
Right. Sorry.
Certainly, like it's not going to make everything branchless. So
yeah.
It's just to make this example slightly easier.
Oh, okay. Sorry.
No, I should have actually explained that, but I forgot. Yep, Jeff.
In the example with the item pointers and just the tuples being read in order. Hypothetically, if we put the item pointers at the end and the tuples at the beginning, would we still be able to see a benefit?
So the tuples at the beginning, did you say?
Yeah, like we put the tuples at the beginning and the item pointers at the end so that the whole still shrinks in the same fashion. Would you see a similar speed up, do you think?
Yeah, I think it would. And I think a lot of databases actually have them in that order. And probably if we could go back in time and do that for Postgres, it might have been a good idea. But I mean, we actually have the flexibility to change the order of the tuples at the end, but we can't swap that with that, right? Because PG upgrade would break, I guess. And
We have bits left in the header.
Oh, so Matthias is saying we've got some spare bits in the header, so we could actually maybe do that. So yeah, maybe we should look into it. Sorry? Okay, right. So potentially we could do that. And we should experiment, I think, and see.
Unrelated question. At the first example where you showed the branchy function, and then you showed that it ended up being predicted well anyway, was that correct? Even with the random positives and negatives intermixed?
So the branchy version, I'll go back to that. Was it?
The one where you took the survey to find out who predicted what?
Oh,
yeah, that.
So this was predicted well with 1,000 elements in the array. You can see all the results. It's better to look at this for the results. So that was the Zen4. So the red line here is what it tested. So down there at the 1,000 element array, it was predicted well, but not so good when I made that array.
And then
100,000 elements.
What pattern was it making use of to predict the branch there? Or maybe if the assembly, you could tell kind of what the assembly was doing so I could understand what pattern it was making use of?
So the reason it was predicted well is, let's go forward. It's probably because of this branch history table. I don't know if that's how the branch predictor works in that CPU, but this is a common way of doing branch prediction. So you can imagine this has probably got like 12, 14 bits in it, and this has probably got enough elements to address all that. It can actually memorize all those patterns up to a certain point. If you had 16 bits here, that would have like 65,000 elements in it. So it could learn that pattern for an array up to roughly that size. And maybe once the array gets even bigger than that, you're kind of relying increasingly on luck. Because some branches might happen to predict the same way, but some you'll get a conflict, and the branch predictor might be wrong. So that's why, which way is it? That's why it gets worse as the array gets bigger. Yeah, so running it 1,000,000 times so that the first loop does the training for the branch predictor, and then there's like 1,000,000 minus one other iterations. Effectively, the branch predictor can just use that previous prediction.
Okay. Well, thank you for the questions. We are at time, so any further questions, please, in the hallway track.
Okay, thanks everybody.
Thank you for your talk, and yeah, give him a round.